So, hello everyone, and welcome to the second Hydroflex webinar. Right before I start, I would like to tell you that we are recording this webinar. So we will post this webinar. There will be a link, and the webinar will be publicly available. My name is Igor Iliev, and I work as a postdoc at the Norwegian University of Science and Technology in Trondheim, Norway. And I'm also the leader of the work package number 3. Today, at the beginning of the webinar, I will briefly introduce Hydroflex, the project, and then I will move on to explain the structure of the work package number 3, which actually covers the content of today's webinar. And then I will invite 2 keynote speakers to present their work within the work package number 3 in Hydroflex. Those are PhD students who are doing their PhD and doing their research within the Hydroflex. And towards the end, I will invite 2 hydropower experts to discuss the topic of today, and feel free to give us your comments and post your questions. So first thing first, Hydroflex. What is Hydroflex? Well, Hydroflex is a project that has received grant from the European Horizon 2020 research program. In Hydroflex, we have 16 partners from 5 different countries involved, and the Hydroflex project is coordinated and managed by the Norwegian University of Science and Technology in Trondheim. What we do, as the name suggests, Hydroflex, we do a focused research on hydropower advancements, and what we're trying to do is to move the boundaries and move beyond today's state of the art in turbine design. So we are trying to look into different methods and develop technologies to improve and increase the flexibility of the current hydropower. The project has started back in 2018 and has a total duration of 48 months. And as you can see, we're somewhere in the middle, or we have passed the midpoint of the project, and we're in the second half of the project, time-wise. The main objective is to combine all research means, starting from theoretical analysis, empirical, numerical analysis, laboratory measurements, and experimental data. So we're trying to combine all these research means with the aim to develop a turbine, generator, and converter as a demonstrator that will be able to handle the future needs for flexibility of the hydropower sector. On the right-hand side, in this graph, we can see the structure of the Hydroflex project. The project is split into 7 different work packages. As you know, today's topic or today's webinar will cover work that is being done under the work package number 3, titled Flexibility of Turbines. For those of you who tuned into the webinar from last week, work package number 2 was covered, and some scenarios and reference cases were defined. And of course, we'll have upcoming webinars that will cover flexibility of generator and converters, and WP3 that is dealing with the social acceptance and mitigation of environmental impact from increased flexibility of hydropower. We also have work packages that are dealing with communication, dissemination, and exploitation of the data and results coming from the project. All right, so WP3 is our main topic today. And in a nutshell, I will describe briefly the structure of WP3. In the work package number 3, we have 5 participants, 5 partners. 3 of them are universities and 2 are industrial partners. NTNU, once again, is the leader of the work package number 3. We have the Luleå University of Technology from Luleå in Sweden. We have the St. Cyril and Methodius University from Skopje, North Macedonia. And we have Rainpower, which is the main Norwegian turbine producer, and their employees have huge experience in the hydropower sector. And they are from, we also have EDR and Medeso, which is a leading supplier of software solutions in the field of computer-aided engineering, once again from Norway. As you can see on this graph, the work package number 3 is also split into 4 main tasks. And so far, most of the work within the Hydroflex and the WP3 has been focused on accomplishing or fulfilling this, the first 2, task 3.1 and 3.2. Task 3.3 and 3.4 are currently underway, and we have started making significant progress there as well. And the work and the results will be subject of future webinars. So today, our presenters will mainly present work from the first 2 tasks in the work package number 3. So task 3.1 has the main objective to develop a design tool, a turbine design tool. And the intention here is to be able to produce an initial hydraulic and mechanical design of a Francis turbine, which is based on empirical relations and simplifications. Of course, all this has to be done in a parametric manner. We're using the Francis 99 reference turbine that is installed in the water power laboratory from NTNU. So we're using this geometry because it's an open geometry that anyone can get the geometry, the experimental data. All that can be found on the following link. And we're mainly focused on the turbine distributor, comprised of the spiral casing, the stay vanes and guide vanes, the runner, and we're also developing a special type of swirl control vanes that will be placed in the draft tube. You'll hear more about this in the next presentations. And everything has to be combined in one computer script that can communicate with ANSYS simulation software. So we decided we're using MATLAB for that purpose. And the MATLAB scripts that are generating turbine designs will be linked with the ANSYS simulation software, such as CFD and FEA. And of course, we have an optimization feedback loop that will search for turbines that have increased flexibility. So the second task, task 3.2, is focused, as you can see on this diagram, is focused on to establishing the software coupling and communication between different software, and provide reliable transfer of mapped data and results. So what we're doing in this task is once the design is being generated by the design tool, we save the design in a special format that is suitable for the meshing software to export it into a meshing software. Then we export the mesh into the numerical analysis part, where we do the fluid analysis and structural analysis. And then after we do a couple of operating points, the results are stored in an output file that goes once again back in MATLAB or other software for post-processing, where we have the optimization function defined to search for the optimal solutions. So all these mechanics and coupling and geometry handling and mesh generation is done in task point 3.2. Task 3.3 is dealing with experimental investigation. So what we plan to do here is we will build turbine design. We'll build a model of the runner and the guide vanes, and we'll do extensive measurements of the efficiency, velocity profiles, pressure and strain under steady and transient operations. And the main idea here, or the main goal, is to provide the project with enough data for calibration or simplification of our numerical methods. So all the measurements will take place or will be carried out in the water power laboratory at NTNU. And this laboratory provides us with accuracy according to IEC international standards. The data will be publicly available as well, so anybody can download it and do their own research on this data and the geometry as well. And finally, the last task in the work package number 3, task 3.4, has the main objective to develop a model for turbine lifetime estimation. So this tool, we're building a tool, a program that will have certain inputs, and then after the calculation, we will be able to estimate the remaining lifetime of the turbine parts. So we're doing a lot of material tests, a lot of welded joint tests. We do fatigue tests with fatigue loads, fatigue cycles. We measure material properties. We will feed in data from numerical analysis for different operating points. And finally, we will try to estimate the remaining lifetime. This is important because, as we know, flexibility or flexible operation of turbines is actually reducing the lifetime of the turbine. So we would like to increase the flexibility of the turbines of future designs, but save the lifetime or increase the lifetime as well. So in a nutshell, that is the structure of work package number 3. And as I said already, today we'll present work from the first 2 tasks under work package number 3. And with this, I'm finished with the introduction part. And now I would like to hand it over to our next presenter, Jesslyn. So I'll stop sharing my screen.